Hi, Algebra 2, period 2. Mr. Walker again. This is Unit 11.2. And so today we're going to look at how we can use exponential equations to solve some word problems. This is going to be a two-part of the notes. So today we're doing part 1, and then Thursdays will be part 2. So part 1 looks at word problems, and there's percents in these problems. And usually when there's percents, when it talks about increasing at a certain percent or decreasing at a certain percent, we're looking at exponential growth and decay. And so our formulas that we're going to be looking at are these two. So y equals a times 1 plus r to the x, or you could also call it t, the t power. Okay, and so this is growth, or anytime we talk about increasing, and that's because of the 1 plus r. All right, and then we also have the other one, which would be y equals a times 1 minus r to the x, or t power. Sometimes you'll see it with a t instead of an x, and the t refers to time, how many years, months, days, that kind of thing. And because of the 1 minus r, this would be a decay problem, or decreasing. All right, so we have an increasing is growth and decreasing is decay. So those are our two formulas that we're going to be looking at and using. And then we're going to also be looking at how we can solve. So most of these problems we're going to be solving for y, but we could also solve for x. And so I'll show you how we can solve for x also. All right, so number 1, Sam bought a semi-rare hockey card for $120. The value is expected to increase 4% a year. All right, so we want to know what each of these numbers represent in our equation. All right, so he buys it for $120. So this is our starting amount, okay, and that's our A. And it's increasing, says it's increasing, so we know this is exponential growth because it's getting bigger. And it's 4% a year. All right, so that's our percent, but we have to convert percents into decimals. So R would be 0.04, right? So that's converting percent into decimal. You can move the decimal, which is to the right of the 4 right now, move it to the left 2 places and drop the percent. All right, so this is R is 0.04. So we can plug those two numbers into our formula because it says write an equation that models this. So y equals 120 times 1 plus 0.04, and we're going to raise that to the x power. Now, you could also simplify inside the parentheses just to kind of clean it up a little bit. All right, so that would be 1.04, the x power. All right, so there's our equation. Now we can use that equation to answer question B. Find the value of the card after 5 years. So 5 years is a time. And so this is t, or we can also call that x. Okay, x. All right, because that's going to be the value for the exponent, and we're solving for the final amount, and that's what y is. Y is our final amount. So we paid $120 for the card. We want to know what its value is going to be at the end of 5 years. All right, so we can plug 5 in for x now. So y equals 120 times 1.04. Okay, we're going to raise that to the 5th power now. All right, so now you do need to calculate. So let's go ahead and get our calculators, and we'll plug that in and see what that comes up with. All right, so make sure you know where your exponent is, your exponent key. All right, so 120 times 1.04, and we're going to raise that to the 5th power. All right, so on your screen, you should get 145.99834. It just keeps going. So typically in money, when there's money involved, we usually go 2 decimal places, unless it tells us otherwise. So we want to go 2 decimal places. So that means we have to look at the 3rd decimal place to see if the 2nd goes up or stays the same. So our 2nd decimal place is a 9, but the 3rd one is an 8. And since 8 is bigger than 5, the 9, which is in the 2nd position, would go up. Right? Now, 9 would go up to a 10, which means the 9 that's sitting next to it, to the left of it, would also go up to a 10, which would mean the 5 would go up to a 6. So this actually would be $146. So that's rounded to 2 decimal places. All right, so now question C. how long will it take for the card to be worth $1,000? So that's our final amount. All right, so we're going to take our equation that we wrote in question A, but this time, this is our final amount. That's our y value. And the question is, how long is it going to take? So that's x, or t times. So we're going to plug 1,000 now into our formula. So 1,000 equals 120 times 1.04 to the x, or t. Now, when you solve this kind of a problem, this is just an exponential equation, and you did solve something like this in the last unit. And so the first step always is to get rid of that number in front of the parentheses, that 120. So we're going to divide both sides by 120. Okay, and then you can simplify that 1,000 divided by 120. So let's see what that is. 1,000 divided by 120. So you're going to get a decimal, 8.33333. All right, so we can go, we'll take it out to like 3 decimal places. The more decimal places, the better. It just gets you closer to what the actual answer is. All right, and you could even leave it as 1,000 over 120 if you wanted to. All right, and that's equal to 1.04. All right, so now when we solve this kind of a problem, we're going to go ahead and log both sides. All right. Now, you could also change it to a log equation. Okay, but if you log both sides, if you remember we did this in the last unit, okay, logging both sides, well, then this exponent x can come down in front. Right, so we have log 8.33 equals x times log 1.04. Now, we're solving for x, so we're going to divide both sides now by log 1.04. Log 1.04. Right, now this is the exact answer. I know it looks weird, but that's the exact answer. But, you know, we want to actually know how many years is that going to take. So we're going to go ahead and use our calculator now and find out what that answer is. All right, so let's go ahead and find our log key on our calculator. All right, so putting all that in the calculator, looks like it's going to be about 54 years. Okay, so we can round this. We're talking about years, 54 years. Nice. All right, so let's go ahead and look at number 2. The population of Cool City in 1988 was 85,000 and has been increasing 3% a year. All right, so write an equation that models this. All right, so in 1988, there was 85,000 people. All right, so this is our starting amount. That's our A. Increasing, so we know it's exponential growth. And then 3% is our R value, but we have to convert percent to a decimal. So R would equal 0.03. All right, so we can plug those into our equation. So y equals 85,000 times 1 plus 0.03. It's going to be 1.03 if you get 1 plus 0.03. All right, to the x power. All right, B, find the population in 2002. So now we have to look and see, when did the study start? Well, the study started in 1988, and now we want to know what the population was in 2002. So we're going to subtract those two values. Okay. For 2002, subtract 1988. So that's going to be 14 years. So our time, or x, is 14. So now we can plug that in, excuse me, to our formula. Y equals 85,000 times 1.03 the 14. All right, so let's go ahead and put that in the calculator. So 85,000 times 1.03. We're going to raise that to the 14th power. All right, so it looks like about 128,570. Since we're talking about people, we'll probably round to the nearest person, nearest whole number. So 128,570. All right, C, in what year in what year will the population surpass 200,000? All right, so 200,000 now, again, is our y value in our equation. So 200,000 is equal to 85,000 times 1.03 to the x power. All right, so now let's go ahead and solve this. So again, we're going to divide by 85,000. All right, so let's go ahead and find out what that decimal is, just to clean it up a little bit. 200,000 divided by 85,000. All right, so 2.35. We'll go 3 decimal places again. 1.03 to the x power. All right, so again, just like before, because we're looking for the exponent, that's our variable, we're going to log both sides. And then the x can come down in front. All right, so we have log 2.353 equals x log 1.03. Then we'll divide both sides by log 1.03. And then we'll go ahead and plug that into our calculator and find the decimal. All right, so putting that in the calculator, it looks like about 28.948. So it looks like if we round it, it's going to be about 29 years. 29 years. And now the question says, in what year is that going to be? So in 29 years from when the study started, which was 1988, we're going to add 1988 to 29 years. And that's going to be in the year 2017. Oops, I need a comma. The year 2017. Okay, moving on. Number 3. According to the International Tennis Federation, a good tennis ball is one that depreciates by 45% of its bounce height each time. You decide to drop a tennis ball from 40 feet. Write an equation. And that models this. All right, so let's see what these numbers represent. We're starting with the ball 40 feet in the air. So this is our A. We're going to start it at 40 feet. It depreciates, so we're going to be using the decay equation. And then 45%, there's our percent, and we have to convert it to a decimal, and so that would be 0.45%, or just 0.45. All right, so plugging that into our equation, y equals 40 times 1 minus 0.45 to the x power. Now we want to clean this up a little bit. Inside 1 minus 0.45, so 40 times, that's at 0.55 to the x power. All right, now B, what's the height of the ball on the second bounce? All right, so we're just going to plug 2 in for x. All right, so pretty easy. Again, we're going to be using our calculator for the second power. So let's put that in. So 40 times 0.55. We're going to raise that to the second power. And so it looks like it's going to be 12.1 feet. 12.1 feet in the air. Now see, what bounce will the height be at 3.66 feet? Right, so 3.66 feet is our ending bounce, our ending amount. So that's our y value. So plugging that into our formula, 3.66 equals 40 times 0.55 to the x power. All right, and so now solving it just like before, we're going to divide by 40. By 40. Let's see what that is as a decimal, 3.66 divided by 40. All right, so it does stop. It just goes out 4 places. So we're going to put the whole decimal because it does stop. Equals 0.55 to the x. All right, so then just like before, we're going to log both sides because our variable is in the exponent, and then the x will come down. And then let's go ahead and divide by this log 0.55 on both sides. All right, so there's our exact answer. And then let's go ahead and put it in the calculator. So the question is, what bounce is it going to be at 3.66 feet? All right, so plugging that into our calculator. All right, so it looks like it's going to be about the fourth bounce. So when you put that in, it's like 4.00011. So that tells us it's going to take it to the fourth bounce. All right, now last one, number 4. Suppose a rabbit population of 10 rabbits double every month. Write an equation that models a situation, find out how many rabbits that there will be after 2 years. Right now, this doesn't have a percent in it. So we're not going to actually use the percent one, the growth and decay, but we are using an exponential equation, and that's because it's doubling. Doubling means we're multiplying it by 2 for each round. So we're going to be using the y equals a times b to the x power formula, exponential. All right, so we start with 10 rabbits. All right, so a is 10. That's a, our starting amount. B, we're doubling, so that's what our B value is. And it says it doubles every month, right? Now it tells us what X is. It says 2 years. All right, so we're going to be using that to solve for the final amount. So plugging the numbers that we have in to just to write the equation would be y equals starting with 10, and we're doubling it, multiplying it by 2 to the x power. So using that equation, we can substitute a number in for x. Now it says, how many rabbits are there going to be after 2 years? But it says it doubles every month. So we have to know how many months are there in 2 years. Well, the number of months in 2 years would be 24 months. All right, so we're going to plug 24 in for x. So y equals 10 times 2 to the 24th power. All right, so let's see what that big number is going to be. All right, so looks like we're going to get about 167,772,160 rabbits, okay, in 2 years. There you go. All right, good luck on the homework.